Hi, I'm Molly.
I'm Caitlin.
I'm Amanda.
I'm Jenny.
I'm Rachel.
I'm Jennifer.
And I'm Emily.
And this is how calculus applies to everyday life.
And you thought this was useless the whole year.
First, we use calculus to make
How
cookies.
do we use calculus when making cookies? So first, you need to start the oven. Sure.
Well, Jenny, it's quite simple actually. You see, we recorded the time at which the oven increased by 10 degrees. By using this chart then, we can find out that the slope, or the oven, is actually increasing at a decreasing rate rather than a constant rate by finding the slope in between each point. As we go down the chart, the slope gets smaller, which means that it is decelerating, or the oven's temperature is decelerating. Does that make sense? Right now, we are recording the temperature of the cookies every 15 seconds, starting right after taking them out of the oven. We are going to see the rate at which the cookies are cooling by proving Newton's law of cooling.
Oops, 45.
So we start with room temperature at 73 degrees, and the starting temperature of the cookies when they first came out of the oven was 213 degrees. Then we used Newton's law of cooling and plugged in the numbers 150 for here, 73 for there, because that was room temperature. The starting temperature here from E to the negative 0.15, that was Newton's constant in this case. And we're solving for how much time it's going to take until the cookies reach 150 degrees, which we decided was perfect cookie eating time. So then we did all the math, and it turns out that 6.5 minutes, the cookies are 115 degrees, or 150 degrees.
We are figuring out displacement versus distance.
Yes.
By
By
calculating
how much
the distance they swing versus the displacement of the swing.
Oh, 102.
35.
109.
28.
116.
22.
120.
17.
120.
15.
124.
13.
126.
10.
129.
Oh gosh. 9.
132.
8.
134.
In this part of the video, we calculated the total distance versus displacement Amanda traveled on the swing. Every time she swung forward, it was a positive distance. Every time she swung backward, it was a negative distance. So by doing this, we got totals for positive distance and negative distance. To get the total distance, we added the positive distance plus the absolute value of the negative distance and got that she traveled a total of 77 feet and 10 inches. Now, this compares to her total displacement, which she actually didn't travel anywhere because she just stayed here on the swing. And so we did that by just calculating the positive distance and subtracting the negative distance to get 1 feet and 10 inches that she actually traveled. But really, she didn't travel anywhere because the swing didn't leave this spot.
All right, ready?
Okay, ready?
Right.
Go ahead.
Go.
I'm just going along.
Yeah, me too.
Okay, so try to stay at this speed then the whole way down. Or we might have to go a little faster.
Oh god.
Oh shoot! Go ahead.
We won't run you over! Go, Nico!
I'm going to do this more than one time.
It's okay, I can.
Okay, what speed are we going at, Emily?
Oh, that's awkward. I could see me in the side view mirror.
What speed are we going at, Rachel?
You guys. 6.
6 miles per hour?
No, make that 10.
It's just I'm riding your bike.
Stop at the stop sign. Stop this time.
Stop sign.
Okay, stop.
45. 45 seconds.
Okay, I'm gonna go around.
Okay, stay at this speed, stay at this speed. What speed are we going?
Okay.
Wait, I can't see them.
What speed are we going?
11.
We're going a lot faster this time.
I think no, it was 10.
Wheels are just gonna fall off.
Oh, there's a car.
Ah, no!
Oh shit. Go forward, Rachel.
Go for it, Rachel.
Oh, dude, 45.
Oh, wow.
Nice.
Okay, in this experiment, we found the distance by using Emily's velocity as she traveled down the hill. So we figured out that it took her 45.8 seconds to travel down from the top of the hill to the bottom of the hill. And she traveled at a constant 10 miles per hour. Then we took the integral of that and found out that she traveled 0.127 miles in that time.
Here we are at Orange State calculating the rate at which you lose money by calculating how much frozen yogurt you put in your cup per ounce.
Is that it? Hurry up. Yeah, it's still recording. Guys, it's been recording the whole time.
Filled in the cup. We first found out the cost per ounce. Then we found here's our volume formula, and we calculated in centimeters. No, with volume, how much the cup was ounces. How the cup converted to ounces with the volume. Then by doing so, we timed how fast ice cream was coming out, and we found the rate at which the cup is filling up is about every half a second, or 0.56 seconds per ounce. So in conclusion, every 0.56 seconds, or about every half second, you lose about 45 cents, or you lose about 90 cents about every second.
In conclusion, we've learned that the only things that matter in life are calculus and golf.
All right.
Rock the